future space missions strive for a high degree of autonomy. Within the Controlling Concurrent Change project, we developed methods for reliable and autonomous system adaptation. The following demonstration highlights some results of the 9 sub-projects carried out by 8 work groups of the TU Braunschweig. In this demonstration, mobile robots are searching for objects while exploring an unknown environment. On the way, the robots are building a map and keep track of their position. Once an object of interest has been detected, the robot approaches it. Then the robot estimates the exact pose of the object for possible manipulation. For demonstration purposes, we use modified turtlebots. To fulfill their tasks, each robot is packed with electronics, among others, a differential drive base, bumper and cliff sensors, multiple cameras, a Wi-Fi antenna, and computation electronics. In total, 4 cameras and additional sensors produce a large amount of processing data. As the robot is battery-powered, a power-efficient high-performance processing platform is required. The Demonstrator contains a Xilinx Link system on chip with a CPU and an FPGA inside. It computes the stereo camera images. An Intel PC is the main controller of the system. Both robots start exploring their environment. The green robot moves much faster than its twin. The speed is limited by the frame rate of processed images. The higher the frame rate, the faster the robot can move around without the danger of colliding with an undetected obstacle. The faster green robot accelerates the execution of computation-intensive tasks in the FPGA fabric of the Zinc. Typically, those hardware tasks would have to be configured in the FPGA at boot time. We can also swap tasks during runtime using dynamic partial reconfiguration. It allows scheduling of hardware tasks within the FPGA, just like software tasks on a CPU. The green robot has already found the blue cup. This is indicated by the blue status light. Its twin with the execution purely in software is still searching. The green robot approaches the object and requests a change for the object pose estimation, which is indicated by a blinking yellow light. The pose estimation requires adapting the image processing chain. Within the CCC project, we developed a multi-change controller, the MCC, which generates a new robot configuration for the new operation mode. This is done in a model domain. The MCC executes multiple transformations of the new functional architecture for the pose estimation. Ultimately, component instantiations are mapped to the platform. Once the MCC has checked all non-functional requirements, the new configuration is deployed to the execution domain. The object pose is estimated from a point cloud which has been extracted from the stereo camera image. This is indicated by a green status light. Hardware acceleration speeds up this process drastically, because even more image processing tasks can be moved from software to hardware. The precisely estimated pose allows to manipulate the object, such as picking it up and moving it. The first object has been found. The robot continues exploration and searches for the next object. Suddenly, the robot signals harsh radiation environment with a red light. Beyond Earth's magnetic field, space vehicles are exposed to heavy iron and alpha radiation. Radiation induces single event effects in silicon. This may lead to undesired system behavior and breakdown. The intensity of the particle flux varies over time, just like weather conditions. The increased radiation makes the current configuration less reliable. The reliability requirement is violated and the robot stops. The MCC now searches for a new system configuration. Restricting the execution of tasks in hardware and temporal or spatial redundancy increases the reliability of the robot. A valid configuration for the new environmental conditions has been found, and the robot resumes its operation. Its speed is reduced because of the added redundancy mechanisms. The robot found the battery pack, estimated its pose, and marked it in its map. Both robots are now jointly searching a red base station where they are supposed to meet. Both still use the hardware acceleration and move with similar speed. The robots made their way to the base station and are going to estimate the base station's pose. Suddenly, a camera sensor required for the task fails on the Gloop robot. This is signaled by the red status light. Such isolated failures should not affect the whole mission. Hence, the Gloop robot reports the problem and the robot agree on a solution collaboratively. The robot can allocate tasks between themselves via a fault-tolerant agreement protocol. The Gloop robot reports the sensor failure. The other robots answer if they can take over the task. The affected robot suggests a new task distribution which is acknowledged by the others. All robots stop for a short period of time while searching for and validating feasible configurations with the new task distribution. This is indicated by red blinking lights. Here, the green robot will estimate the base station's pose and transfer it to the Gloop robot. After estimating the pose of the base station, the green robot also needs to locate the Gloop robot in order to transfer the estimated pose in the correct coordinates. The base station's pose is then transmitted and appears in the map of the Gloop robot. The mission can proceed. When exploring planets and other objects in space, smart, distributed and collaborating robots are necessary. Those systems need to react autonomously to changes such as environmental conditions or failures. The methods developed in the CCC project for safe in-field dynamic functional adaptations of hardware and software will facilitate such future autonomous space missions.